Great. Thank you so much for the invitation and for the opportunity to talk about interfaces and mixing and 3D printing technology. My name is Dan Ilyin. I did my undergraduate studies at Caltech in physics and chemistry, graduated in 2020, worked with Professor Bill Goddard on many different projects. Today I'll be talking about physics-based modeling of reaction kinetics, the process that we called RMD2Kin, where we looked at what happens at the molecular level, and then looked at how that contributes to possible phenomena at the radical interface. Now I am a third-year PhD student at Stanford in mechanical engineering. I'm working on additive manufacturing of micro devices, and the second half of my talk will be about that. So, for context, the idea behind reactive molecular dynamics to kinetics was to have correct reaction chemistry in large-scale simulations. So in order to do that, we require good kinetics information. So we need to know the energy barriers, the reaction rates, and mechanisms, ideally with quantum mechanical accuracy, because if we have the wrong kinetics, then our simulations will also be wrong, and any sort of information that we get about the reaction front, including any potential instabilities that could form there, would not necessarily be correct. The difficulty in obtaining kinetics for more condensed systems is that empirically you can calculate kinetics using quantum mechanics for simple systems, or you can run experiments, but usually those are gas phase experiments, which are much more dilute, and the liquid phase kinetics could be quite different. So the paradigm was that we had access to a very good force field called ReaxFF, which was a reactive force field developed by Audrey van Duyn, also in the Goddard group, which would essentially give quantum dynamics accuracy for these molecular dynamic simulations. And so after that, we would go in and analyze the bonding interactions and then extract kinetics rates and mechanisms on the scale of 10 to 100 nanometers, with the next steps being envisioned to input into continuum dynamics on larger scales, and then get information about real-world performance of the system in much larger quantities than what can be simulated on a computer. So this bottom-up approach yielded immense detail about the system. So by going from quantum mechanics through this reactive force field into atoms and bonds, and then into defining each species, and then tracing the species throughout the simulation, we would get reactions, and then from reactions we could get kinetics, and that we would get a very high level of detail about the system. So as an illustration, I will show here results from decomposition of hydrogen peroxide. So this is one of our simulation cells, and if I zoom into this region there, from the molecular dynamics simulation, because this is a reactive force field, you actually get information about bond breaking and formation in real time. So that you could see individual reactions. For instance, this one is a hydrogen peroxide molecule reacting with an OH radical to form an HO2 radical and water. And then in a different corner of the box, we can zoom in and see an HO2 radical reacting with a hydrogen peroxide molecule to form oxygen, water, and reformed OH radical. And then there were interesting interactions such as this temporary rotational interaction between two OH radicals where they would collide together, spend some time spinning, and then go back out and separate. And there were other interesting reactions as well, such as an HO2 radical combining with a hydrogen peroxide, and then using another hydrogen peroxide to essentially transfer a hydrogen from one molecule to another. So this system looked had 1,000 molecules in it at a density of 55 kilograms per meter squared. So this is quite a bit higher than dilute gas phase reactions. We looked at a temperature range from 1,000 to 2,000 Kelvin, where the reaction would happen readily and quickly. And then after setting up the molecular dynamics simulation and analyzing all the interactions between the atoms and signing bond orders and defining molecules, whenever a product was formed, like I showed in the previous slides, I would be able to go back in time and find the interaction that formed it. And these were all individual labeled interactions. So each one of these interactions had a number, each atom had a number, and each molecule had a number. And then if a complex was formed, I would wait for it to decompose and then analyze the reactants and products. And from that, I could define the overall reactions, analyze the reactions at each time step, and extract the rates, energies, and reaction barriers. So in order to go from these concentrations, which is essentially the information that I had directly from the simulation, I knew how much of each molecule or each species there was in the simulation at any point in time. I would be able to go to rates and figure out the dominant reactions. So rate is given by a reaction constant times the concentration of each of the reactants, and then these were all first order reactions, so the exponents were 1. And then the temperature dependence, because as I mentioned, we looked at a range between 1,000 and 2,000 Kelvin, was given by the Eyring-Polanyi equation, which is an Arrhenius-like dependence, which gives us insights into the entropy and enthalpy change and free energy change of the reaction. So from this information, I was able to see that there were 7 dominant reactions, and I was able to calculate the delta H and delta G of the transition state. And this is exactly the kind of information you need to input into continuum dynamic simulations to run these larger scales, larger scale simulations in order to describe a more real world system. So, and the very cool part about this was that it was all self-consistent. So looking at the Eyring plots, which is essentially a rearrangement of the Eyring-Polanyi equation in order to form a straight line, we would see that all the reactions fit on the predicted line, and then using these delta H and delta S numbers and plugging them back and sort of back calculating from just the initial conditions where we had 800 peroxides and 200 OH radicals, and just plugging that into a continuum a formula that would be used in these continuum dynamic simulations. We see that both the predicted and the actual rates shown in the simulation box coincided pretty well throughout the simulation. So the dashed line is the calculated concentrations from the barriers, and solid is the observed in silico concentrations. So after this, we also looked at what would happen if we concentrated all these radicals in one place, sort of to form a combustion interface, or a 3D printing interface, as you will see in just a few slides. So this was a bit of a larger simulation, also using lamps in the React force field. It wasn't a constant temperature bath, it was a ramp where we would concentrate all the radicals in one place and then increase the temperature and look at the propagation. And so at this density, which is about the same density as in the previous simulation, we saw some hints that there could be these radical sort of fingers or divots in the reaction front propagating into the bulk. And then our thought was due to the density by over a few time steps, tens of time steps, the rest of the reaction front would kind of catch up to these outshoots. And so this was an interesting interesting idea to look further into, but I graduated, so I went on to do my PhD, where I'm doing I'm looking at 3D printing and interestingly still looking at reaction fronts and radicals and interfaces. So as a brief overview, 3D printing, it's a very active area of research. There are lots of hobbyist style 3D printers, which essentially melt plastic and deposit it into a shape of your design. I'm looking at what's called fat photopolymerization 3D printing. So this is more on the industrial scale. It enables single step production of geometries that would otherwise be impossible to produce with conventional manufacturing methods. And compared to something like injection molding, where you have a set mold and you create tooling to create a specific part, the complexity in this process is essentially free, because the same printer, the same device, can produce whatever part you choose as long as it can print it. Specifically, I'm working on continuous liquid interface polymerization and applying that to high resolution 3D printing. So this is an interfacial and radical driven 3D printing process. It's been, over the past about 7 years, it's been proven to be industrially scalable. And it can produce a wide range of materials with different properties. On the screen here, on the bottom, you see an Adidas shoe that's produced in the millions, if not tens or hundreds of millions. And that midsole, the lattice, is 3D printed using this exact process. So some of these materials that can be 3D printed with clip range from really stiff resins, really high temperature resistant resins, to really soft and elastic resins, and also biocompatible resins. So the range of applications is really quite large. So let's talk about the high resolution aspect, because that's what I'm working on. On the left here, you see a diagram of a high resolution 3D printer, and on the right is a picture of the printer that I built. So on top, you have a Z stage, and it's a vertical stage that moves with submicron precision. On there, we have attached a build platform. There's a resin vat, which actually contains the resin, and then some optics to focus light, and the light is coming from a UV light engine. And UV light engine is essentially just a fancy word for a projector that projects light. It much like an overhead projector in the conference room, except it projects a very small image with very high pixel density onto resin and in UV, but otherwise it's a very, very similar process. So if we zoom into to what's happening at the build platform and vat, when the build platform lowers into the vat, it reaches this window, and this is probably the most high-tech part of this process. The window is actually oxygen permeable, and so when UV light hits the resin, it induces polymerization. So UV light cleaves molecules and creates radicals, which then allow the resin to polymerize. But because the window is oxygen permeable, there is a dead zone where the oxygen concentration is too high, because the oxygen essentially takes those radicals that are forming at the interface and it's consuming them. So instead of propagating the reaction and interacting with other monomers, the reactants are essentially quenched. The radicals are quenched. And if we zoom in even more, we can make this plot of radical concentration versus oxygen concentration, and then look at the concentration of monomer and converted oligomer in the dead zone. And why this is important is because this liquid interface, the dead zone, is continuous throughout the print. So at no point during the printing process, if your parameters are all correct, does polymerization actually occur at the window. And so what that allows is it prevents the part from ever sticking physically to the window. So if you think of other 3D printers that, for instance, other vat polymerization 3D printers, many of them use essentially just a glass window. And if you've ever used like UV curing epoxy or another kind of UV polymerizable fluid, you know that if you bring two objects very close together in the gap, we're talking about only 50 to 100 microns, if not less, and then shine UV light, and those two objects will stick together. But because our window is oxygen permeable, the part only sticks to the build platform, and then it's easy to take off. And so this is actually the key aspect that allows production of the flexible parts and also the dual cure resins, which are all very fragile and easy to break if they were adhered to both the build platform and the window. So as you can imagine, this is a process that needs to be very finely controlled. So one of the first things is light control. You want your light to be focused, and you want each pixel to be resolved. And our pixels, the native pixel size of the projector is about 7.56 microns, which is right about the size of a red blood cell. And then we use reduction optics. So essentially a microscope objective put in reverse to shrink that image down 1 or 2 or 4 times in order to get pixel sizes of 4 microns or less. The important part here is to to know that your objective can actually resolve each individual pixel. For instance, not all commercially available microscope objectives will be able to resolve each pixel due to their Rayleigh criterion, where their numerical aperture would be too small. So the other part of light intensity is light over penetration. So the resin permits UV light to go through, and if your intensity is too high, or there's not enough UV absorber in the resin, for instance, light will cure not only the layer that you want, but also the previous layers. And so you will be left, instead of, for instance, this I-beam shape, you will be left with an overcured blob on the bottom of each overhang. And so you have to control that very precisely. And we can control that by adding more UV absorber into the resin so that the penetration depth is about the same size as our layer height. And we can also control that by flowing resin through, which are both techniques that we've written papers on, and they're under review right now.
So like 5 minutes?
Sorry?
Like 5 minutes?
Thank you. And the other light control aspect is where you would essentially grayscale in order to achieve a smooth surface. So instead of just turning on a pixel or turning off, you would gradually decrease the intensity over subsequent layers, and that would yield a smooth surface. So this is another slide showing light over penetration and utilizing what we call dynamic print controls, where the light exposure is adjusted for each individual layer to prevent this Z overcure from occurring. The other aspect of this is stage motion. So when the resins are quite viscous, they're about the consistency of honey, some of these resins. And so the resin needs to be static when you're projecting, because if it's not, you essentially flow your uncured parts or partially cured parts away from your part. And so there is quite a bit of parameter optimization involved here, where you would want to move the stage and then wait, and then for the resin to stop moving, and then turn on the UV light, and then as soon as the UV light turns off, you move the stage again. Or you could also do what we call pumping, where you pump the stage higher than your layer height and then bring it down gradually, and that allows another level of control over the resin flow. And so just to illustrate what happens if you don't wait enough, you actually get this sort of canyoning feature shown on the bottom left, where you would where your resin literally creates canyons in your part. If you wait long enough, then your part comes out as you want. So here are some parts that we were able to produce, and this is interesting to us in applications for medicine and for microelectronics. And I will briefly mention that these we're able to print these microneedles that can deliver drugs through the skin to the area that has a high concentration of immune response cells. And then we're also looking at creation of microelectronics parts through 3D printing these small structures and then metallizing. And so this is an area of active research. And I'd like to thank all of my collaborators in the Goddard group as well as in the Simone group. And I will be happy to take any questions. Thanks so much for your attention.
Yeah. Let us applaud the speaker. Questions? So what are the potential applications of this technology?
Yeah, so the potential applications of this technology are, we're looking heavily into the medical field because there is a need for a lot of devices that can be customized at the micro scale. For instance, I mentioned these microneedles, which have been an active area of active research for many decades now. But due to manufacturing limitations, they haven't been as successful as we had hoped. And it's essentially a device that can deliver vaccines into the skin instead of intramuscularly. And that has quite a bit of benefits compared to intramuscular injection due to the biology of the skin.
Other questions? Questions from the virtual audience? And just for information, what is the typical size of the object that you can print, like microns, submicrons?
Yeah, so the resolution that we've published on is about is a single-digit micron, so anywhere from a few microns to 8 microns features, and then we've been able to produce smaller features than that as well, but not nanometer scale. So we have not we're not submicron yet.
Okay, so submicron is a overarching goal. Okay, thank you so much. So let us applaud our speaker. Thank you.